Finally, in our census of the contents of the universe, we come to the one that's the greatest mystery of them all, the dark energy. I can pretty much condense this lecture into 2 words. Nobody knows. But let's elaborate a little bit. Just to remind you, various cosmological tests imply that about 70% of the critical density of the universe is made out of this mysterious component. Its effects are to accelerate the expansion of the universe. This affects the age of the universe and therefore may also affect the growth of density perturbations that give rise to the large-scale structure. It is an effect that's only apparent at large cosmological distances, which explains why it hasn't been seen earlier. And it's certainly an outstanding puzzle, and not for the lack of trying. As you'll see later, many people have tried. So sometimes we talk about cosmological constant, which is just one possible form. A more general form of dark energy is called quintessence. I'll define that in a moment. The plot on this slide shows succession of probability contours for what the values of density parameters of matter and vacuum, which is dark energy, could be as a succession of different experimental constraints. As you can see, they condense to the value that we always quote for the concurrence cosmology. Again, to remind you, the classical origin of the cosmological constant was essentially as an integration constant in Einstein equations. It simply comes out of general theory of relativity, but the theory does not specify its value. For that matter, the theory doesn't specify the value of the Newton's gravitational constant either. And you could think of that as a new constant of nature, whose value is something that we should probably determine observationally. Since energy density implied by cosmological constant is constant in time, it corresponds roughly to the force that is proportional to the distance, like the elastic force. You can think of it as the elasticity of the physical vacuum, although in this case, it actually is the spring that expels. The sign convention is such that positive value of cosmological constant, which contributes to the positive mass energy density, is repulsive force. The first attempt to really understand physically what's going on was due to the great Soviet astrophysicist cosmologist Yakov Zildovich. As early as in 1967, he proposed that this must be related to the physical properties of the physical vacuum. Now, in Einstein's days, vacuum was vacuum, but the quantum physics told us that vacuum is very much alive, that's filled with virtual particles and antiparticles that form and annihilate on timescales that are consistent with uncertainty relationship. The existence of these virtual particles has actually been experimentally confirmed in an indirect sense through a thing called the Casimir effect and also through some subtle effects of quantum field theory. So you can think of cosmological constant or dark energy as the ground state of the physical vacuum of the entire universe. Now you may also recall from your quantum physics that if we know that something is the ground state, we cannot tell what the value of that is. And if the universe is in some higher energy level state, it can decay to the lower energy state, and that's exactly the mechanism proposed for the inflation. So in some sense, inflation is all about cosmological constant, but not the one we have today. If indeed dark energy is a product of quantum processes, and it is obviously an aspect of gravity, we need quantum theory of gravity in order to understand it. We do not have such a theory yet, and nevertheless, people have tried. Now that has led into what's probably the single worst scientific prediction of all time. And it goes like this. Remember Planck units? Well, those are units composed of physical constants, and so you can evaluate what's the Planck energy density. It turns out the number you get is 123 orders of magnitude higher than what's actually observed. Well, that's a little bit of an embarrassment. Now, physicists could think of ways of producing such energy density, but then you have to cancel it. And it's very hard to come up with a mechanism that will cancel it, not exactly, but to one part into 10 to the 123, which is called the fine-tuning problem. Now, the obvious conclusion of this exercise is that this is a completely wrong way to try to explain it. Nevertheless, for some reason, people thought, well, if it's not this, it must be zero, which is pretty much like saying, well, I can't tell what it is, therefore let's pretend it doesn't exist. It wasn't a very strong argument. It simply said, we don't know how to compute it yet. Nevertheless, it was decided to ignore it, more or less, even though observers keep saying that, well, maybe there is some evidence for it. Most theorists pretty much decided that it must be zero until the evidence became so strong that it had to be really taken into account. So let me make the distinction here. Dark energy could have many different functional forms as it comes to, say, function of time or distance or expansion factor. And if it's constant in time, if it's a constant energy density, then it is cosmological constant. But a more general case is the case where it changes in time. That's called quintessence, and in the language of the equation of state, it implies that a little parameter w is a function of time. So we know from observations that it's pretty close to constant and maybe absolutely constant. But there is some room for its variation, and if it does vary in time, that will be a very valuable hint for what physical mechanisms might be. Now, there is something called the coincidence problem, which basically says that, isn't it remarkable that we live in time of history of universe where the energy density of vacuum is comparable to one of energy density of matter? I don't find this to be a very strong argument, because through most of the history of the universe, this was the case. Now, usually, people who insist on this problem plot things on a logarithmic axis, or log of time, or log of the expansion factor, and then you can squish this diagram all you want. And so then it does indeed seem like this is a very special time where the two curves of omega matter, omega vacuum do cross. But this is purely an artifact of plotting things in a logarithmic axis. If you plot in linear time or linear expansion factor, well then, most of the history of the universe was like this. This doesn't remove the puzzle. And indeed, this really is an outstanding challenge for theoretical physics. There are many different models that have been proposed. There are probably thousands, literally thousands of papers trying to explain it. But most of them fall in one of the several categories. Many assume that there is some sort of quantum field that decays, just like happened in inflation. So this would be the second inflation. The physical origin of this field is completely unknown, and it's very much ad hoc. It was invented just to make cosmological constant today. Another approach is to modify theories of gravity in a more serious fashion than, say, Mond, this time completely consistent with theory of relativity. And there are models that predict that. There is a very interesting class of models called holographic theories. And they essentially relate the value of vacuum energy density to the area of our horizon. And this is part of a much deeper physical understanding of the origin of era of time and entropy. But there is still not a single model that is universally accepted. String theory has come up with the idea of cosmic landscape. And the idea here is that there are many universes. Remember the multiverse from inflation at ours is just one of the many universe bubbles inflating in a bigger universe. That's entirely speculative, of course. And moreover, it's a priori untestable. There are ways in which you can estimate that the number of independent universes with different physics is 10 to the 500 power. And the idea is that physical constants are a random draw, and they differ from universe to universe. And we just happen to live in one in which cosmological constant, as well as any other physical constant, happen to have these values. I do not find this terribly compelling because it's purely ad hoc, and it's also a priori untestable. And one of the important characteristics of science is that it has to be testable. There are also models that connect dark energy and dark matter, and so on and so forth. But the fact that we have thousands of them tells you that we don't have a single one that's any good. So one possible path forward is to find out if the vacuum energy density changes in time. And there are many experiments and surveys currently designed to try to measure precisely that. So far, all the results are consistent with truly a constant energy density. Here again are some of the observational results. These are again probability contours, this time in the plane that shows equation of state parameter W, which you may recall is exactly -1 for the case of cosmological constant, plotted against other cosmological parameters, say omega matter. And different observational constraints overlap, condensing probability contours. So maybe this measurement is not to 1% level, it's maybe a 10% level right now, but they're always consistent with the case of cosmological constant. Still, some variation in time is allowed, and better experiments will confine it even further. This is a slightly different version of that plot. This time, W is plotted against the energy density of the vacuum itself. Again, error ellipses overlap and all zoom in onto the region where vacuum energy density is about 73% and W is exactly -1. But the case is still open. So there you have it. It's still a mystery. It's a wonderful physical problem. Hopefully someday we will actually solve it. But to recap, this is what we know about the composition of the universe. Its overall energy matter density is close to the critical, to within measurement errors of about 1 or 2%, and maybe absolutely equal to it. Of that, about 73-74% is in the form of dark energy, the rest in the form of matter. Of that, only 4.5% or so is in the form of baryons, and the rest is in some as yet unknown form of non-baryonic matter. And among the baryons, only like 0.5% is in form of visible stars, and the rest of it is probably hot gas. So it's quite remarkable that all of the universe that we actually do see is only 0.5% of its total matter energy density content. Next week, we'll talk about structure formation in the universe.